Hey, quick question. Right now, as you're watching this video, your computer is executing millions of instructions per second. But here's the thing most people don't realize. Those instructions are shockingly simple. Like, embarrassingly simple. We're talking add two numbers simple. So how does something that basic produce all of this? A browser? A video game? An AI? That's exactly what we're unpacking today. Stick with me, because by the end of this video, you're going to understand what's actually happening inside your computer, and it's going to change how you think about every program you've ever used. Here's our roadmap. We're going to start with how computers are built, the physical parts that handle data. Then we'll look at how computers remember things, memory, registers, all of that. Then we get into the really cool stuff, machine language, the secret code your processor actually understands. We'll walk through how a program actually executes, step by step. Then we'll look at the math and logic your CPU does under the hood. And operations, bit shifts, all of it. And finally, we'll connect all of this to something you might actually write yourself. Python code. No prior experience needed. Let's go. All right, let's start with the big picture. The part of your computer that actually does stuff, that processes data, is called the CPU. That stands for Central Processing Unit. You might also hear it called the processor. Back in the 1950s, a CPU was literally a room full of electronics, racks of machinery, spinning reels, the whole deal. Today, it's a flat square about the size of a postage stamp. In your phone, it's even smaller than that. And because they're so tiny, we call them microprocessors. Now, inside every CPU, there are three key parts. Think of it like a tiny office. First, you've got the Arithmetic Logic Unit, or ALU. This is the calculator. It does the actual math, addition, subtraction, and it also handles logical comparisons like, is this number bigger than that one? Second, there's the control unit. This is the manager. It doesn't do the math itself. It tells everything else what to do and when to do it. Third, and this is really important, there's the register unit. Registers are tiny, super-fast storage slots inside the CPU itself. Think of them like sticky notes on a desk. If you're in the middle of a calculation, you don't want to go all the way to the filing cabinet every time. You keep your notes right there in front of you. Now, the CPU is connected to main memory. Think of that like your filing cabinet. It holds a lot more data than the registers, but it's slower to access. The connection between the CPU and memory is called the bus. It's basically a highway for data. Here's the key thing to understand about why registers exist. To add two numbers stored in memory, the CPU can't just add them in place. It has to load them into registers first, do the addition, then store the result back to memory. That's actually 5 separate steps just to add two numbers. We'll come back to that in a minute. One more thing. Many machines also have cache memory. Cache is a small, super-fast chunk of memory that lives inside or very close to the CPU itself. It acts like a shortcut. Instead of going all the way to main memory every time, the CPU keeps a copy of the stuff it's using most right now in cache. It makes everything run faster. Cache memory is typically just a few hundred kilobytes, but it dramatically speeds up how fast the CPU can crunch through work. Okay, here's one of the most important ideas in all of computing history. It seems obvious now, but it wasn't always. Early computers were built for one job, like an old mechanical calculator. You built it to add. That's it. You couldn't just reprogram it to do something else without physically rewiring the machine. Then came a breakthrough, and it's actually a little controversial who deserves credit for it, but the idea is often associated with a mathematician named John von Neumann. The idea was this: what if you stored the program in memory, right alongside the data? Instead of the instructions being baked into the hardware, you encode them as bit patterns and put them in memory. Then, the CPU reads the instructions from memory, one by one, and executes them. To run a different program, you just change what's in memory. No rewiring required. This is called the stored program concept, and it's literally the foundation of every computer that exists today. Your laptop, your phone, your smart fridge, they all work this way. Here's a cool side effect of this. Since programs and data are both just bit patterns in memory, a program can manipulate other programs. It can even modify itself. That's how compilers work. That's how operating systems work. That's honestly how AI works at a very basic level. Now, let's talk about machine language. This is where things get really interesting. Every CPU is designed to understand a specific set of instructions. We call this its instruction set, or more formally, its machine language. An instruction in machine language is just a pattern of bits, ones and zeros. The CPU looks at that pattern and says, "Oh, I know what to do with this." It's kind of like how different notes on a piano trigger different sounds. Each bit pattern maps to a specific action. Now, here's something surprising. The list of instructions a CPU actually needs is surprisingly short. Once a machine can do a few well-chosen basic tasks, adding more doesn't make it theoretically more powerful. It just makes it more convenient. This has led to two different design philosophies. One school of thought says, keep it minimal. Only include what you absolutely need. This is called RISC, Reduced Instruction Set Computer. These chips are efficient, fast, and cheaper to manufacture. ARM processors, the kind in basically every smartphone on the planet, are RISC chips. The other school of thought says, give the CPU lots of complex, powerful instructions, even if some of them overlap. That's CISC, Complex Instruction Set Computer. Intel processors in most laptops and desktops are CISC. Both approaches have trade-offs, and they've competed for decades. But regardless of which camp you're in, machine instructions generally fall into three categories. Data transfer instructions. These move data around. Load something from memory into a register. Store something from a register back to memory. Copy a value from one place to another. These are called load and store instructions. Arithmetic and logic instructions. These are the calculations. Add these two numbers. Compare these two values. Flip some bits. These live in the ALU. Control instructions. These are the ones that let programs make decisions and repeat things. Jump to a different part of the program. If this condition is true, then skip ahead. Without these, a program could only run straight through from top to bottom, one time. Now, how does an instruction actually look? It's a bit pattern, typically broken into two parts: the opcode and the operand. The opcode is like the verb. It says what to do: store, load, add, jump. The operand is like the noun. It gives the details. Which register? Which memory address? In the example machine language from one of our textbooks, each instruction is 16 bits long, 4 hexadecimal digits. The first digit is the opcode. So an instruction that starts with 3 means store. An instruction that starts with 1 means load from memory. An instruction like 35A7 means store the contents of register 5 into memory cell A7. Hexadecimal is just a shorthand for binary. Instead of writing 16 ones and zeros, we write 4 hex digits. It's the same information, just way easier to read. Okay, this is the part that ties everything together. How does your CPU actually execute a program? The CPU runs on what's called the machine cycle. It's 3 steps, repeated over and over, thousands of millions of times per second. Step 1. Fetch. The CPU looks at a special register called the program counter. The program counter holds the memory address of the next instruction to execute. The CPU fetches that instruction from memory and loads it into another special register called the instruction register. Then it bumps the program counter forward, ready for next time. Step 2. Decode. The CPU examines the bit pattern in the instruction register. It figures out the opcode. What kind of instruction is this? And it parses out the operand. What are the specifics? Step 3. Execute. The CPU carries out the instruction. If it's a load, it goes and fetches data from the specified memory address into a register. If it's an ADD, it fires up the arithmetic unit with the right registers. If it's a store, it writes a register's value back to memory. Then, back to step 1. Fetch the next instruction. Decode it. Execute it. Repeat. The speed at which a computer does this is measured by its clock speed. Your computer has an internal clock, an oscillator, that pulses at a regular rate, coordinating all of this activity. Clock speeds are measured in gigahertz today. Gigahertz. 1 gigahertz means a billion cycles per second. But here's a nuance. Clock speed alone doesn't tell the whole story, because different processor designs do different amounts of work per cycle. That's why we use benchmarking, running the same real program on different machines and comparing how long it takes. Let me walk you through a concrete example of program execution, because it really clicks when you see it step by step. Say you've got a tiny program stored in memory starting at address A0. The program loads 2 numbers, adds them, and stores the result. Here's what happens. The program counter says A0. The CPU fetches the instruction at A0. Let's say it's 156C, which means load register 5 with the value at memory address 6C. The program counter advances to A2. The CPU decodes. Opcode 1, load from memory. Operand, register 5, address 6C. Execute. Pull the value from memory cell 6C into register 5. Next cycle. Program counter says A2. Fetch 166D. Load register 6 with the value at memory address 6D. Same deal. Now register 6 has its value. Next cycle. Fetch 5056. Add the contents of registers 5 and 6 as 2's complement numbers. Leave the result in register 0. The ALU fires up, does the addition, puts the answer in register 0. Next cycle. Fetch 306E. Store the contents of register 0 into memory cell 6E. Done. Final cycle. Fetch C000. That's halt. The machine stops. 5 instructions. That's a complete program. Your computer does this millions of times a second for every single thing you do on screen. Let's zoom into the ALU. What kind of math and logic does it actually perform? The obvious stuff: addition, subtraction, multiplication, division. But here's a fun fact. Multiplication is really just repeated addition. Division is repeated subtraction. Some very simple CPUs only implement add and subtract, and derive everything else from those. But the ALU also does logic operations. These operate on bit patterns directly, 1 bit at a time across the whole pattern. There are 3 main ones: AND, the result bit is 1 only if both input bits are 1. Think of it as both things must be true. Or, the result bit is 1 if either input bit is 1. At least one thing is true. XOR, exclusive OR. The result bit is 1 if the input bits are different. One or the other, but not both. These sound abstract, but they're incredibly practical. One major use is masking. Imagine you've got a byte, 8 bits, and you want to isolate just the lower 4 bits. You AND it with the mask 000011111. Wherever the mask has a 0, the result is forced to 0. Wherever the mask has a 1, the original value passes through unchanged. It's like putting a stencil over the data. Or works the opposite way. It's great for setting specific bits to 1 regardless of what they were before. XOR with all ones flips every bit. That's how you get a bitwise complement. It's also used in encryption. XOR a value with a key to encrypt it. XOR again with the same key to get back the original. The ALU also does shift and rotate operations. Imagine the bits in a register are beads on a track. A shift moves them all 1 position left or right. The bit that falls off one end either gets discarded, that's a logical shift, or gets placed at the other end. That's a circular shift, also called a rotation. Shifting left by 1 position is equivalent to multiplying by 2. Shifting right is dividing by 2. This is a super fast trick that compilers use constantly. Okay, you've been learning about ones and zeros and machine instructions. Let's bring it back to something you might actually write. When you write a Python script, you're not thinking about registers or opcodes. Python shields you from all of that. But the connection is very real. Every Python statement you write gets translated eventually into sequences of those machine instructions we just talked about. Python's plus and minus operators, those map to the ALU's ADD and subtract instructions. Assigning a variable, that's a load or store. A conditional if statement, that becomes a conditional jump instruction. Python also has direct equivalents for those bitwise operations we talked about. And is AND. Vertical bar is OR. Caret is XOR. Right shift shifts bits right. Left shift shifts bits left. So if you write x equals 0, b100111010, and 0b11001001 in Python, those 0b prefixes mean binary, Python will perform a bitwise AND on those 2 patterns and give you the result. Exactly what the ALU does. The if statement creates a conditional jump. A while loop is the CPU executing the same sequence of instructions over and over, checking a condition each time to decide whether to go around again. And functions? Those map to a mechanism in machine language where the CPU can jump to a sequence of instructions, execute them, and then jump back to where it came from. That jump to a subroutine and return pattern is fundamental to how all programming languages work. One practical difference in Python, it's dynamically typed. That means Python figures out what type of data a variable holds at runtime rather than compile time. This is convenient, but it's also why Python can sometimes give you a type error that surprises you. Like if you use input to get a number from the user, Python gives you back a string, not an integer. If you try to do math on a string, the CPU literally doesn't know how to add it, because the bit pattern for the string 4 is completely different from the bit pattern for the integer 4. You have to explicitly call int to convert it first. What we covered today, the CPU has 3 main parts. The ALU does the math, the control unit manages operations, and the register unit provides superfast scratchpad storage. Main memory holds more data, but is slower to access. Cache memory sits in between, speeding things up. The stored program concept, the idea of storing both programs and data as bit patterns in the same memory, is the foundational insight that makes modern computing possible. It's why you can run different software on the same hardware. Machine language is the set of instructions a CPU actually understands. Each instruction is a bit pattern with an opcode, the action, and an operand, the details. Instructions fall into three categories: data transfer, arithmetic/logic, and control. The machine cycle, fetch, decode, execute, is the heartbeat of your computer, repeating billions of times a second to run every program you use. The ALU performs not just arithmetic, but logic operations, AND, OR, XOR, shifts, which are the building blocks of everything from image processing to encryption. And all of this connects directly to high-level languages like Python. Those simple, readable statements you write are ultimately translated into the same kinds of machine instructions we've been talking about all video. Here's the big insight to take away. Computers are incredibly fast, but also incredibly literal. They follow simple instructions, one at a time, exactly as given. The sophistication of modern software isn't because the hardware is magic. It's because millions of these simple operations are organized intelligently, at blazing speed, through clever layers of abstraction built up over decades. That's what makes computer science fascinating. If you want to go deeper, try writing some bitwise operations in Python. Play with AND masking. Write a tiny loop and think about what machine instructions it would translate into. The best way to understand this is to get your hands dirty. Thanks for watching. If this was helpful, hit like and subscribe. It genuinely helps the channel. Leave a comment with any questions. I read every one of them, and I'll see you in the next one.